So we need to have some kind of chemical reaction to provide us some context, so I've decided to use a pretty famous reaction. It's the Haber process, the one in which we make the material ammonia that we use to fertilize our food when we grow it so that we don't starve to death. So there's hydrogen, there's nitrogen, there's ammonia, a nice formation reaction here back from when we were learning about delta G. This is a delta G formation reaction. And you'll notice here that I'm able to write down not just A, B, C, and D. I'm actually able to write down the starting concentrations of hydrogen, nitrogen, and ammonia, and the equilibrium concentration of each of these. And now I'm ready to do my work. What are some of the questions that I might ask? I'm going to show you about 4 different kinds of problems that you might work involving this Rice expression. I'm going to start off with a couple that we never really ever use because they don't have any practical value, but they give you a sense of how the Rice expression works. And then we'll move on to the ones that we're going to use over and over again in doing our calculations. Now, the first thing I'm going to do is tell you what the answer to what K is. K is equal to 3.8. It's what happens at equilibrium when I take ammonia and I divide it by hydrogen times nitrogen. What this is telling me is that because K is greater than 1, this reaction happens. This is telling me that delta G is negative. This is telling me that ammonia is stable. These are all these things I remember from back in thermodynamics. But it's important to be told this K value here because it immediately allows us to start to work different kinds of problems moving forward. And in fact, what you're going to see with the Rice expression is that there are basically 2 kinds of questions. The kinds of questions where I give you K and say, what is everything in this table? And the kind of questions where I give you what's in this table and you have to tell me K. So I can go back and forth between these values. Do understand, though, that because this is a course in chemical equilibrium, I'm far more concerned with K than I am with Q. And my ultimate goal, as you will see soon enough, is to work with K exclusively, understanding that that value of 3.8 must occur because it's the ratio of this ammonia squared over hydrogen cubed times nitrogen. That whatever else happens, these 3 values here have to fit into this equation such that the answer is 3.8. Welcome to the simplest kind of equation involving the Rice expression. I call it simple because, in fact, this is the first thing they teach you to do in high school chemistry. It is utter fiction in terms of the way that the real world works, but it's a nice introduction so you have a feel for how to work the problem. Notice that what I'm telling you here is that I don't know K. Actually, we know K. It's 3.8, but we're going to pretend we don't know it right now. And I'm going to tell you that nitrogen's 0.1, hydrogen's 0.5, and ammonia is 0.057. Those are the values I'm giving you. The first thing your brain should be thinking is that is an equilibrium value because it's in brackets. I'm not giving you capital C's. I'm giving you equilibrium amounts. At that point as well, you should know also that this is probably fiction because it's a lot harder to know what the equilibrium amounts are than to know your starting amounts. Think about it. You want to know what your starting amounts are, you go get a half a gram of sugar off the shelf, you go get yourself 2 pounds of ammonia off the shelf, and then you put it in water, you know what the starting concentration is. But to know the equilibrium concentration, to know these values down here, you would have to go in at equilibrium and swim around down there and use some spectroscopy or something and find out what the result is. And there are people who do this, but it's not an easy thing to do. It's much easier from a practical perspective to know what you're starting with. But in this work of fiction we're doing, because we're learning about K, I'm telling you that these are my values. So what you're going to do is come down to the Rice expression, and if you're using the Rice expression correctly, you know that you need to put in a value for 0.5, 0.1, and 0.057 down here, just like they told you to. And now that you know these values, you can ratio them. 0.057 squared divided by 0.5 cubed times 0.1 is equal to 3.8. What do you know? K is 3.8. This is a combination of numbers that make this work. Now, you should understand that there are lots of combinations of numbers that could make that work. Here's another combination. I could have hydrogen equal to 1 molar, nitrogen equal to 1 molar, and ammonia equal to the square root of 3.8. Notice then it would be the square root of 3.8 squared, well that's 3.8, divided by 1 cubed times 1, well that's 1. So K is equal to 3.8. Just like when we were learning about that house party, I can have lots of different equilibrium concentrations depending upon who crashes the party, but they must, when it's all said and done, equal this number 3.8. Anyway, this is problem type 1. It's the simplest one there is. I'm not sure I ever actually put it on an exam in a college chemistry course, but it gives you a sense of what the equilibrium values are and how they relate directly to K.